so another perspective is until I came to the Redmond and David thought I was really stupid.
Okay, let's start. So I want to talk about the last, announcements first. So we're going to switch from doing homework on Wednesdays to shorter homeworks every class period, which is important because you guys need to be practicing what we're doing before the next class. So waiting till Wednesday every week for this next module is not going to be as advantageous as having shorter homeworks every class. So that being said, then the Friday's homework is posted. It's both a short written and a short online. This is nothing like the assignments you've had due Wednesdays, okay? So make sure there's both written and online due Friday, 9 a.m., okay? 9 a.m. Friday morning. Okay, so be aware of that. And so this was from the homework due this morning. This is the last problem, the Cobra spring. And backwards. And what is the force required to hold a spring x centimeters past its natural length? What was that? Remember? Nick knows. Anybody else? What's the force required to hold a spring past its x centimeters or x meters past its natural length? Yeah. K times x, right? So it's proportional to how far you're stretching it, right? So what does that mean for if you're stretching a spring? What does that mean for the force that you have to apply as you stretch it? It's constant force as you stretch it? No, this is saying that it requires more force the further you stretch it. So it's your force is gradually increasing as you stretch the spring. Okay? So in the Cobra spring, so in a normal spring, this is constant, right? This is constant in a normal spring. But in the Cobra spring, K was also a function of X. Okay? So constant for standard spring. But then we at the end of class, we said that the Cobra spring is a function of X. So it has variable. So not only does the force change, as you stretch it or compress it, but the constant itself is changing. Okay? So in order to, and we know that the rate of change of work is force, right? So as you stretch a spring, you're doing work. Okay, and so the rate of change of that work is the force, and the force itself is increasing. Okay? So that means that our work function is going to be the force function. But for the Cobra spring, we found that the K value itself was variable. But then to get the force, you need to multiply K times X, right? The force is K times X. So that was the rate function. That was like the first question in that problem, the last problem on the web work. That's okay. So then it asked, so the spring itself was 0.3 meters or 30 centimeters, and then we're gonna push it all the way. That would be 100% of the work would be to push it all the way down. So how would I figure out 100% of the work if it's 0.3 meters and I'm going to push it all the way down? What would the work be? What would I enter in? Yes, sir. That's right. So that's all the work it's going to take to push that thing flat, push that spring flat. So because we're displacing it 0.3 meters, or the whole length of it. We're pushing it, we're compressing. Okay. So then it said, how much how far would you have to compress it to achieve 50% of the total work? So what's a way, how can I represent here 50% of the total work in a way that I trust? I know for sure this is 50% of the total work. What could I write in here to do that? Yes, sir? Right, so I'm going to take that answer and divide by 2. We know for sure this is half of the work, right? Half of the work. Guessing based on the length is guess. We don't really trust that. We know things are changing as we're compressing this. Okay, so that's half of the work. And so now the question is, how do I figure out how far to compress it to get half the work? Am I going to compress it halfway? No, because force is changing, and on top of that, this spring constant is changing. So there's no way that pushing it halfway is going to give you half the work. Okay, so how do we figure out how far to push it to get half the work? So looking at this, can I take 2.5875 and plug it in for W? And then what would I be doing? I'd be trying to find out what X was. What's the problem with that? Yeah, open form is like a big roadblock here, right? Open form is preventing us, because it doesn't compute things readily, it also doesn't lend itself to algebraic manipulation, right? You can't plug in a value of W and then do some algebra or some arithmetic to solve for X, right? This open form is kind of, it doesn't lend itself to computing, to doing algebra. Yes, sir?
So could you take the antiderivative of f of t and then set that equal to 2.5875?
Yeah, we haven't learned that yet. Yes. So what else could we do with what we've learned so far in our class? Yeah, Dylan.
I would graph the function w, so y equals w from 0 to x, x is less than 30. And then I would also graph y equals that 2.5875
Okay.
intersection.
So yes, right, with the tools we have so far, if we could use GC, we could graph that. And I have that already there. So from 0 to 0.3, so I can graph that and then get a better view of it. Something like that. Okay, and then what do you want to do?
I would graph, so y equals, and then what you have is blue right there, yeah. So we should get a horizontal line. And then just find that intersect, and then the x value is what we want.
These values of work on the graph, are they x values or y values? Those values of work that I'm calculating. Those are y's, right? The dependent variable is work. For x is the number of meters compressed, right? Compressed. So that's why I want to set that half of the work to a y value, and then I'm gonna come in here, and I want to zoom in. Maybe I'll select this graph instead. Can I do that? Do that. So here. There we go. And I want to pinpoint that. So I'm looking for y value of 2.58 with my shaky fingers and my bad eyes. Let's see here if I can get close. 2.5. All right, just zoom way in, so we're really close. Okay, and so then x value is 0.229, and this is still like an approximation because I might not be right on that, but that gives us an x of 0.229 meters. So I'm going to compress it 0.229 meters, and that's going to be half the work, right? Further than halfway, right? Halfway would be 0.15. We know that the force resisting is increasing, so that makes sense that half the work would be more than halfway compressed. So 0.229 meters. Okay, so we're forced with open form to do something else, use some kind of like method like graphing or guess and check or something like that. And it's even so now it's still not precise. Like it's I'm pretty close here, right? So I'm off by like 1/10,000th or 100,000th or something. But still, it's estimating, it's zooming in, it's or guess and check. And so what we'd like is, what would be very helpful here is closed form. If we had a closed form of this function, rather than open form, that lends itself to computing, solving, rearranging, algebra, okay? So that's where we're going next here in the course, is given now that we've written lots of open form net accumulation functions, can we then change those into a closed form that allows for computability and solving things like this? Okay, questions on this example? So let's do one more spring thing. This one. So just skip over to this new question, right? So to skip over the top part. New question, it takes 50 joules of work to stretch a spring 0.08 meters past its natural length. How much additional work would it take to stretch it from 0.08 to 0.13 meters? So I want you to define variables, make sense of the problem. And then no, we're not gonna, I don't want you to calculate an answer, but just then set up a mathematical statement or statements that would lead us to answering this question. So we're going to define variables, we're going to understand the question, and set up the math to model this, right? Set up the math to model what's going on here. Take a minute or two and see how you do. So this is kind of a test to see if we understand springs. If we understand how springs work, we can set this up. Yes, sir?
This is a normal spring now.
Yeah, thanks for asking. That's yeah, this is a standard spring. Okay, where's Jesse? Jesse here today? Jesse, did you make any progress, Jesse? Yeah? W of AX, okay.
Equals the integral from a to x
Okay.
of kt.
True statement? Is it right? Okay, do you go any further than that? So now we want to kind of start applying the numbers here.
Oh, yeah. We can put 0.08 into
Yeah.
a and 0.1.
You want to put 0.08 here and 0.13 here. Okay. And so that will be the additional amount of work. And then am I ready to solve that, to get the additional amount of work? Can I solve that? You're shaking your head. Tell me. In the black t-shirt.
Okay, so.
So first of all, do you agree with this?
Yeah, I agree with that.
Okay.
But first you got to define your spring constant.
Okay. So we need K.
To do that, you can set up the force equation, which would be, Fx equals to Kx.
Okay.
And you can plug in 50 for the force, and x for that one would be 0.08 meters.
Okay. All right. So let's see. Where is Hunter? Where's Hunter? Is Hunter here? Yeah. What's that?
That was
Oh, that Hunter Villa. Hey, Hunter Villa? Hunter Villa is in the back. Okay. Well, that was weird. Okay. You agree with that, Hunter? To do 50 equals k times 0.08 to solve for k.
Yeah.
Agree with that? Uh-oh. Some people are saying no. You say no.
Well, 50 is the work, not the force.
Okay, so first of all, 50 is a work.
So it would be force times distance would equal, or no, force would equal kx. So the work would equal kx times x. It would be force times distance.
Force times distance.
Distance is x. So
Okay.
kx squared.
Okay?
And then you do 50 equals kx squared. X is 0.08. When you divide 50 by 0.08 squared.
What about this? You agree with this? Someone else say no?
I don't know.
Oh, you don't know. Okay.
Could you just skip finding k altogether and just do work equals force times displacement? We have a displacement, we have a work value. So we would be able to find out our constant force.
I'm not sure what you mean.
Because we have 50 joules equals F times 0.08. We'd be able to do 50 over 0.08 to get a force, and then work, and additional work would be
0.0.
work equals the 50 over 0.08 times 0.05 is 0.13.
Okay, so you're saying work equals force times distance, and the force is, or the work is 50, and so equals force times 0.08. How about this? Agree with that? Okay, so maybe we haven't quite learned about springs yet. This doesn't work. Why not? I know almost everyone in the first class tried to do it too. What's wrong with this? Yeah.
The spring constant wasn't taken into consideration.
Okay. Okay, that's, yeah. Yes, sir.
Is it because that's the value at 0.08, not the accumulation in 0.08 of work?
Okay. And so when work accumulates, what happens to the force as it accumulates? When you're stretching a spring, the force increases. What does this equation say? Yeah, this is assuming that the force is constant over the distance of 0.08 to get 50 joules. The force is changing. Force changes. You can't do this. You can't do this because force changes as you stretch. So what does 50 equal? Bigger. I need a bigger eraser. So we need K. We can't just use linear. We can't just use force times distance. What does that 50 joules? How would that 50 joules be calculated? Yeah.
From the integral of 0 to 0.08
Mm-hmm.
k kt.
There we go. Accumulated work by a spring, we have to use a net accumulation function because the force changes. It's always changing as you're pulling. So you can't just use force times distance. That force times distance assumes a constant force. So if we need K, we've got to solve this. Doesn't make sense, right? So accumulated work from a spring requires integral net accumulation of work because that force is continually increasing as you pull on the spring or compress it, whatever. All right, so we need K. How are we going to get K? We need to solve how are we going to get K? Easily? Here we are again, right? Here we are again. What's our problem? Open form. So if we had some kind of closed form, we could solve for K, right? Open form does not lend itself to computing, algebra, working on it to solve for a variable. So again, more motivation. So we'll put that on hold, right? We'll put for what, and even a graphing solution would be difficult or not straightforward here to figure out what the constant is inside the integral there. Okay, so even graphing it here would take some ingenuity. It's not straightforward. Okay, so questions on that. But this is what determines k, and once we have k, then we can put k in here and figure out the work to go from 0.08 to 0.13.
Could we use substitution?
Oh, we're getting there. Okay, so we're getting there. All right, here we go. So getting closed forms from open forms. So first of all, let's answer this. What's the net accumulation of a quantity given by a function f starting from x equals a? So I have some quantity function f, and I want to write that as, I want to write the exact net accumulation starting from x equals a. Let's see here, where is Micah? Where's Micah Ban? Micah? Can you tell me the net accumulation of a quantity? If f is the total accumulation, what's the net accumulation starting from x equals a? Okay, so net accumulation is integral, right? Integral from a to x of what? So if f is our total accumulation and we want to write a net accumulation of f starting from a, then it'd be the integral from a to x of what? Of f? No? The rate of change, right? The rate of change. So it's our standard net accumulation function. So if f is the total accumulation, then the net accumulation starting from a would be the integral from a to x of the rate of change of f dt, or t dt. Okay? Familiar? Hopefully very familiar. So now, how can I use that to express the total accumulation function? So this is the net accumulation function. How can I use this to express the total accumulation? Where, Juliana?
You could add the initial value.
Yeah, how do we express the initial value? Good.
You could do like f of x. I mean, the function from a to x of f of x plus.
So you just wanted to add the initial value. What's that?
F of a plus the integral.
Good. So it's f of a plus the integral. If it was 0 to x. So this is starting from a to x. So if we're going to start accumulating from a, then to get the total accumulation, we need all the accumulation up to a, not necessarily 0, unless a was 0. Does that make sense? Okay, so here's our total accumulation function. We've seen that before. And I'm going to subtract a from both sides. And so now that left-hand side is equal to the right side. So that left-hand side is another way to express net accumulation. So they both sides now express net accumulation or net amount of change, but in different ways, right? So they each kind of represent a different way of thinking about exact net accumulation. On the left, it's like the idea of final minus initial. It's like everything up to x minus everything up to a gives you how much change from a to x, right? And then the right side, we know is the like accumulation of bits of change, right? So it's not, so a lot of times students get caught thinking that we're accumulating the rate. We're not accumulating the rate. What are we accumulating? Small changes, right? So this is like dy, right? dy, because it equals m dx. So we're accumulating small changes in the quantity. And we're finding those small changes using the rate. Okay, so watch out for thinking that we're accumulating the rate. We're not accumulating the rate. We're using the rate to gather up compute changes, and then we're accumulating those changes in the quantity. All right, so then if I change the order, then that should look familiar from Calc 1. You recognize that?
Yes.
What is this? Fundamental theorem of calculus. So this is what the fundamental theorem of calculus. It's showing us two ways of the net accumulation function. And so the fundamental theorem is a huge part of writing closed form. So this right-hand side for us is going to be closed form of this because they're equal. So all we need then is we need f. How do we get f, right? So if we have the open form, that means we have the rate of change of f. How does the rate of change of f relate to f? It's derivative, right? This is the derivative of f. So if I had the rate of change, I'm looking to find antiderivative, right? So I'm trying to find the antiderivative of my rate function because that function's derivative is what I'm given, right? So I know that that's the derivative of f. So this is a means of finding antiderivative. And so our theme with antiderivative, as we learn these antiderivatives, the emphasis is going to be, let's know our derivatives so good that we can do them backwards. So let's know the rules so well that we can do them backwards, instead of trying to learn new rules for antiderivatives. Okay, instead of trying to learn new procedures and new techniques, let's just know derivatives so well and that we can think and do them in reverse. Okay, so that's going to be kind of the way that we treat that. Okay, so here's our closed form accumulation. It's about two things. It's about the fundamental theorem and then knowing antiderivatives. If we can apply the fundamental theorem and know how to do antiderivatives, then we can write closed forms from open form net accumulation functions. So we got some exercises here, and for each one, we're going to explain I'm going to show you some expression. We're going to explain the meaning of the expression, just to practice that, keep reviewing that. And then we're going to write a computable expression that gives its value exactly. What am I talking about in part B when I say write a computable expression that gives its value exactly? What am I saying? Saying closed form. I say find a closed form. And then if that closed form can be simplified, then we want to simplify it as appropriate. Okay? So before we do that, I want to just add an intermediate step in here. It's kind of the transition from t back to x. So when we find the antiderivative, that's the f function, we're going to write it still in terms of t. And then we got this bar on the right, which means what we see to the right there. So this thing means plug x into the function, plug a into the function, and subtract just like this. So we kind of don't have to try to do that all at once. Change it to x and write that out. So first we'll do the antiderivative and write it in terms of the variable in the integral. And then we'll plug in the x and the a and subtract. Okay? So we'll do the first one together, and then you guys will get to work on these others. First one here. So we're going to apply the fundamental theorem, and it means that we need to know the antiderivative of cosine of u. So what we're asking is, what function, if we took the derivative of it, would we get cosine of u? Nice, easy one to start, right? Sine of u. Now it's not negative sine of u because we're not taking the derivative of cosine. We're asking what function has a derivative cosine u. So that's sine u. And so then I'm going to say, all right, I'm going to evaluate that at x and negative a half and get the change, right? Get the amount of change. So that means sine x minus okay, so question. This new expression, sine x minus sine of negative 1/2, what does that mean, or what does that find for us? Deanna, is Deanna here today? She's not here. Chance. So this new expression that I just found, what is its meaning?
It's the antiderivative.
Okay, so sine u is the antiderivative. I guess we never did part A, right? We never did part A. We never answered what is the meaning of that expression. So let's go back and do that. Yes, sir.
From negative 1/2 to x, it gives the accumulated value of cosine u from negative 1/2 to x.
Okay, so does it give the accumulated value of cosine u from negative 1/2 to x? Agree with that? Are we accumulating cosine u? What is cosine u? It's the rate of what? It's the rate of change of what? Some quantity, right? So we're modeling some quantity, so it's the rate of change of some quantity, right? And so this then is the net accumulation from negative 1/2 to x of some quantity whose rate is cosine.
Yeah, sine.
Okay? But it's not sine because it's sine minus sine of negative 1/2. You see that? So, and we want to think about this as modeling some real world quantity like volume or mass or temperature or something like that. So we'll just leave it open, right? So if there's some quantity in the real world this is the net accumulation of that quantity starting at negative 1/2, and we know the rate of change of that quantity is cosine u. Okay, so now come over here. What is the meaning of this? What does this one over here mean? Yeah.
How much it's changed?
How much has changed?
The negative 1/2 to
Okay,
x.
right. How much the quantity has changed from negative 1/2 to x? Which is what? Isn't that what this was too? Isn't this how much the quantity's changed from negative 1/2 to x? And what's the rate of change of this function? Cosine. So the meaning of this is, what's that? No, the meaning of this. How does it compare to the meaning of this? Exactly the same. It's exactly the same. It's the net accumulation of some quantity starting at negative 1/2 to x, and that quantity's rate is cosine. Cosine x. Okay? The difference is, what's the one big difference? Closed form. We can compute with this, right? It's convenient for computing and spitting out lots of values of rapid fire values of net accumulation. Okay, your turn. So I got 3 more. So start by interpreting the meaning of the expression, then write it in closed form using antiderivative and using the fundamental theorem, and then simplify it if you need to. Okay, go. And I'll be calling on you to tell me your progress after a little while. If you've got a question, ask one of us, ask Matt, ask me, ask someone around you. Let's regroup. Where's Alexis? Regoza? Did you make any progress? So Alexis, What is the meaning of that expression right there? Can you tell me? Shh, okay.
I kept on getting it confused. Basically getting the derivative, but I can't explain it, but I got it.
But no, I'm asking about part A, the meaning. So what's the meaning of that? What does that expression represent?
Isn't that just the antiderivative and
No,
derivative?
like
That's
no.
how I was doing it in the beginning.
But I'm not talking about solving this. I'm talking about as itself. It represents something without. We can never do any solving of this, and it has a perfectly legitimate meaning. Yeah, Nick.
It would be in this case it would be the total accumulation just because we're starting with 0, but it would be the net accumulation of some quantity with a rate of 3 e to the w.
Okay. Now, so it's not total because it starts with 0. Because notice this one started at -1/2. So there could have been accumulation in the negatives. So we don't know what's going on in the negative, like negative values. So we still want to say a net accumulation, right, of some quantity, and the rate of change of the quantity is 3e to the w, right? So it's the net accumulation starting from 0 of some quantity whose rate is 3e to the w. Okay, and so then what do we need? So we're going to apply the fundamental theorem, and we're going to use thinking about what function did we learn in Calc 1 that has the derivative 3e to the w? What function in Calc 1 did we learn has the derivative 3e to the w? So this was the e exponential function, e to the something, has that special quality that it has its own derivative. So the antiderivative is 3e to the w in this case. And then that's going to be from 0 to x, and then we just plug in the x, plug in the 0, and subtract. And when you plug in the 0, you get 0, right? Then why in the test do you plug in 0 and get 0? Don't do it on the test. If there's a 0 there, plug it in and chase it out. Make sure it's not 0. Many of you on the test are going to look at that 0 and go, oh, it's just the first term. Trust me, it's going to happen. Don't do it. Don't be one of the ones. Okay? When you plug in 0, you get 3. You don't get 0. Okay, next one. Let's see. Where's Justin Smith? Justin.
Here.
All right, tell me. Antiderivative.
The antiderivative is t to the 5th power over 5.
Okay, so the power rule for derivatives means the power did what?
It added on, and then we added on a fraction.
For derivatives. When you take the power rule for derivatives.
Oh, minus 1, and then times it by the previous.
Right, so the power goes down 1 in the power rule, right, when you take the derivative? So in the antiderivative, it's going to? Add 1. But then you're saying we need 1/5.
Yeah, because whenever you do the derivative, you always have to multiply it by the original
Right, because the actual derivative of t to the 5th is 5t to the 4th, but we don't have a 5 here, right? So I need the 1/5, so I just get t to the 4th when I take the derivative of that. From 1 to x, 1/5, x to the 5th is the easy part. Just plug in, subtract. Okay, now, so this next one. So our goal is, and this is in your homework too, don't apply substitution in the homework as well. We want to look at this and say, what function has this as its derivative, right? So what function has this as derivative? What rule would have been applied here to get this derivative? Anyone notice? Notice 2a is the derivative of a squared, the inside. What rule is that from? Chain rule. So we're going to think about, when you have the chain rule, you chain on the derivative of the inside, so then when you go antiderivative, it's going to disappear. It's going to collapse back inside and disappear, right? So what will we have then? So the 2a will be gone, and it'll be a squared plus 3 to the, you're going to add 1 to the exponent, just like in the previous one, we added 1, but then we're going to need 2/3. See how much faster that was than all that use substitution? If you could just recognize that that's the chain rule, it's chain rule derivative, and work it backwards. But we're going to practice all next time on that. Okay? So if you're still a little shaky on that, don't worry. And then plug in 10. I think you get 103. Do you get 103 right there? Okay, so we're asking what function has as its derivative the rate function I'm given. And then I'm going to apply the fundamental theorem and do final minus initial. So that antiderivative evaluated at x minus the antiderivative evaluated at the starting value. And that gives me the net change from whatever a is to x. Okay, one more, quick. Any questions before I erase? Does this look familiar? So now we're asking, we're going to apply to get a closed form. We're asking what function would have its as its derivative kx. K comes along for the ride, so we're just actually asking what's the antiderivative of x. It's like x to the first. So we're going to add 1, because we're doing the antiderivative power rule. We're going to add 1, and then divided by 2, 0 to 0.08. Plug in the 0.08, plug in the 0. Now this time, you plug in 0, you get 0, right? Not every time though. Check it. You got to check it every time. And we know that equals, that was the 50. And so now we can easily solve for k. Why? Because we got a closed form for that net accumulation of work.